Okay, hello. Let's start into the ME773 Project 1. So I'm Jack Pockabeer, Pock Abeer. I'm a second year mechanical engineering graduate student. My research professor actually is Dr. Derby. Uh, the research I do here primarily focuses on the food, energy, and water nexus, where I look at microfluidics, heat and mass transfer, and wettability. So off to the right, you can kind of see uh, visual abstract of the research I've done, where you can see the red is a water droplet that we placed into a simulated soil pore and looked at some of the effects that this changes in the soil pore had on evaporation. To continue the introduction, some of the hobbies I have, I used to run track and field for K-State here, so I enjoy running and lifting weights. And also, I'm decently big into chess. So if you have the spare time, add me on chess.com at jackpack. Always trying to improve my elo. So getting into the actual project, here is my actual potato off to the right in the oven. I used to bake it. The dimensions are also listed here. I measured the surface area by covering the potato in saran wrap, one layer thick, and then unwrapping it and then physically measuring the surface area that way. I got the density alpha and K from Kumar et al. They had a paper, I think, called Thermal Transitive Properties of the Russet Potato. So that's perfect for this paper. With some of these numbers, I could actually get the volume for my potato because I didn't have a way to submerge it and measure the actual volume. So using Kumar's density for potatoes and also the mass that I took by just weighing it on a kitchen scale, I could solve for the volume. Also, with this, I could solve for the characteristic length, which we'll need for the BO number listed here. So for number one of the project, we need to look at the BO number because if the BO number is less than 0.1, then it is a reasonable assumption. This basically just means that convective heat transfer dominates. Uh, so looking at this, this is an assumption based off of free convection of air, where I set H equal to 5 watt per meter squared Kelvin. This, I think, is reasonable. However, it could be slightly higher or lower. Generally, this is for free convection, and I think around 5, based off what everything I've looked up, is reasonable. Also, I got the potato-specific heat at constant pressure uh, listed here from another reference, Hayes. So actually, with all this that I've listed and shown so far, we have everything to solve for part one. So starting out, we look at the first law and look at the internal energy. We get du dt equals q dot minus w dot, and then where we can slash w dot right off because there's no boundary work. Then going to the next line, we can see that m c sub p dt dt equals our convection term. You can add in a radiation term here. However, for this case, we are not going to do that. We're going to neglect radiation. I actually think in this case, radiation should not be neglected. That's because the T S to the fourth minus T SIR to the fourth is, maybe I had those backwards, but it's because the oven is so hot and the ambient temperature of the potato is not so hot, the radiative Q dot is not negligible. However, if we were to implement that here, it leads to a brutally hard, maybe not brutally hard, but brutally hard for me integral, and I couldn't solve it. So we're just going to neglect radiation. Then we look at the lump systems approximation. That's the whole point of looking at our BO number that allows us to use the lump systems approximation. And basically with that is we set the surface temperature of our potato equals that temperature throughout the entire potato. So it's not dependent on the position that you would be inside the potato. With this, we can then integrate this equation and solve for T, implementing the proper integration bounds as well. These derivations that I'll go through are in more detail in the paper that I'll submit alongside these. So you can see our equation for time here. In the experiment I'll do and talk about later in this presentation, I set the oven to 232 degrees Celsius, or 450 on my actual dial. My ambient potato temperature, my T initial, is just the temperature of my house, which is at 68 degrees Fahrenheit or 20 degrees Celsius. So plugging everything that we know in here, we get a temperature cook time to reach our 99 degrees Celsius fully cooked potato, 55 minutes. And so upon first thoughts, seems very reasonable. So let's see what the other methods give us. So for part two, we're looking at 1D transient conduction. We want to start with the heat equation and then think one-dimensional, no volumetric heat generative term. It's transient and it's an infinitely long cylinder with axial symmetry. So just with that right there, we can simplify the heat equation down to this. We are in polar coordinates, and our two terms are just gone based off just being 1D, no heat generation term, volumetric heat generation term here, and then it's transient off to the right, the storage term. From here, we can, to make this PDE going to be a lot easier, we cannot get a non-dimensionalize with this theta, where theta as a function of R and T is our temperature minus our ambient temperature. So we're going, since this is a partial differential equation, we're going to need an initial condition and some boundary conditions as well. So for the initial condition, this first one, it's basically at time equals 0, it's just a function. We'll have just a function of radius, or function of R in our potato. Then for the first boundary condition, we'll have that the temperature distribution in our potato is finite, meaning we'll have actual numbers somewhere, and that at any time, our potato's temperature is not going to be an infinitely large value. And then for the last one, we look at a conduction term and a convection term, and that R naught, or the surface of the potato, the sum of these is 0. Continuing on, we'll need to use separation of variables, where we combine these into two functions, which are just, one is just a function of R, and one is just a function of T, this capital gamma function. And knowing this, we'll have a solution of form here, where JO is a Bessel function, I believe. And looking at this, this has a characteristic value equation, or characteristic value lambda n with positive roots. We can then form this into a transcendental equation, rearrange this, where we get this equation shown here. So continuing on with this, again, these are done better in more detail in the accompanying paper I'll turn in with this. But continuing with these initial conditions, the Fourier number, equation for centerline temperature, gamma sub n equals lambda n R naught, and these boundary conditions that I mentioned in the previous slide, we can get the equation we need. Finally, we'll implement the one-term approximation, which I'll talk about in this next slide, and analyze the centerline temperature of our potato. So for the one-term approximation, this needs to be when the Fourier number is greater than 0.2. So we'll solve for this Fourier number to see if this is allowed to do this. Also, going back to this infinitely long cylinder assumption, generally this works for length of your cylinder over the radius of your cylinder for greater than around 10. And in my case, using the dimensions of my potato, we got it to be about 2.45. So already some of the things baked into this approximation, this time that we'll get is dubious based off this. So this is what the equation after everything gets to. Look, this is kind of can also be known as theta star. Plugging everything that we know into these equations, and then we'll actually have to using our BO number, we'll have to consult table 5.1 in the book, and this will give Kasai, I think it's called, and this will give our C1 constant as well. Having all this, we can just solve for our Fourier number, and I get this is 5.59, which is much greater than 0.2. Having that in, we look at the definition of the Fourier number, and it has time in it. We just solve for this t, and putting everything in there, we get a grand time of 10.4 hours. I believe everything was correct that I've done here. However, I'm pinning the majority blame on this infinite cylinder assumption that it would just not be reasonable in the case of my. At Dillon's, I tried to pick the long and most cylinder-like potato, but compared to an infinitely long cylinder, very short and stubby. Continuing. So for part 3, I created an actual experiment to see the real life results that we could compare to these equations. So we needed to reach 99 degrees Celsius. Off to the left, you can see my experimental procedure. First, we needed to preheat the oven to 450 degrees Fahrenheit, which is my 232 Celsius, with the rack in the middle. Then once you're up to temperature, insert the potato directly onto the rack. And then my plan was to monitor the temperature every 10 minutes, all the way up until it is fully cooked. So some things in this temperature monitoring, whenever I would open the oven every 10 minutes, I'd place the gauge in the same spot each time and let the temperature gauge come to it settle at a certain temperature, not that it was still increasing. And then also, while I was doing this measuring, I wanted to do this procedure as quickly as possible. And I'll mention some of the sources of experimental error that could come with my experimental procedure. Also, you can actually see up here some of the work that I was doing earlier when I talked about in the lump systems approximation, that radiation term being a bear. So having this convection term here minus this radiation term, we would then want to separate it, get like variables on each side. So this dt is obviously an easy integral. However, you get this guy over here, and that is a bare integral. I couldn't do it. So, go back. Some of the results I saw is that it took about 57 minutes for my potato to get up to all the way to the temperature of 99 degrees Celsius. This should have been 60 minutes following exactly my experimental procedure here. However, when I saw that it was at 93 at 50 minutes, I kind of assumed it would get there before 60 minutes. So I opened it a little bit early at 57 minutes, and is a good guess. So just a little bit of comparison. These results are extremely consistent with part 1, the lump systems approximation, 55 minutes for that, compared to the 57 minutes I got from the actual experimentation. So some of the factors affecting experimentation accuracy, first of all, something that you could consider is that conduction through the oven rack is ignored. That may not be something that you can ignore because this heating rack is going to be very hot as it's been warming up in the oven for this whole time. Also, what I think is the greatest source of error for this experimental cooking time is, since we have to measure the temperature of the potato, constantly opening this door is going to let all the hot air out and significantly decrease the average oven air temperature. I think that's a big consideration. And then some things like human error, sensor error, and also oven error are some other considerations, like, is my oven actually at 450 degrees Fahrenheit? Who's to say? Sensor error with my Walmart temperature gauge. Who's to say that's exactly extremely correct? So some things like that. And then for the final part of this project, let's model this potato cooking simulation in ANSYS. So first of all, I'll just kind of walk through the main steps to do it. I had always learned ANSYS Fluent. That was the first thing I learned last semester, but instead of Fluent, you need to use ANSYS Thermal Transient Package. So your first step would to be make a potato material. So basically you can just type in a potato as your material and give certain things like your specific heat at constant pressure, your K, and your density. So then the first step would be to create a geometry. For me, I created a cylinder that had the radius of my potato at its thickest part, and the length of my potato. From there, you would create a meshing, which I'll talk about in a little more, and then set your initial temperature and add a convection temperature addition. Then you'll need to create a temperature output solution. And also I created a temperature probe little blip, and this is for later grid independence testing. So I ran my analysis for 7,000 seconds, which I thought was plenty of time for my potato to get cooked. And looking at the information I got to reach 99 degrees Celsius, which this was doing it all in Kelvin, so I converted it to Kelvin. It took about 4,881 seconds or 81 minutes. This is some of the actual pictures that I got from this. The blue line is what I'm taking my information off of. So this blue line is the average temperature of my potato. So you can see at about 4,800 seconds, it was at, I think, 372 Kelvin, which equaled my 99 degrees Celsius. Also, this is a picture of my actual potato as the cylinder, and you can see how hot parts of it got over the course of 7,000 seconds. So the center was still not completely as hot. Meanwhile, this was at like 420 degrees Kelvin or something like that. So I guess I can go back and talk about this result a little bit more. So 81 minutes, I think that is a reasonable time. So for the first lump systems approximation of 55 minutes, I neglected radiation. I also neglected radiation here. However, I think that would be incredibly easy to add. And I think adding that radiative term into ANSYS Fluent would make this a much more accurate simulation and bring that 81 minutes down to something more like 60 minutes or something that we'd actually see when I bake the potato. So just something I thought of. So after my first run of the simulation doing this, I got my results, but I wanted to make sure that my results weren't dependent on my meshing size. So this is kind of some of the work I did here, a little bit of graph of my grid independence. So you could see it's not very dependent on it. I mean, this is 421.1. This is still 421.2. This is the final temperature in Kelvin. So I thought it was a fine thing to measure my grid independence off of. So I hiked up my grid number to, I think it was around 70,000. So this actually kind of took a while. A little bit of my rookiness showing. So I mentioned why radiation wouldn't have been hard to add in ANSYS, and that's kind of why my radiation time or my simulation times are a little bit long. But I think these results are still fairly in agreement with part one and experimental results, besides my part two, that was like 10 hours. So here's two of my references that I had for my potato properties, and that's it. So thank you for listening and following along. Also, like and subscribe. Stop share.